So we know at this point that if I have a charge, let's just say it's positive. So I have a positive Q. If it's negative, then we just reverse the direction of the electric field lines. Right? So if it's positive, I can draw the electric field due to this charge, and it'll point radially away. And as we talked about before, we can indicate the strength of that field by drawing more or less lines. If I want to know the strength of the electric field at a certain point in space, then I draw that field line, and I can calculate it based on the distance, just like with Newton's law of universal gravitation, the distance r. Technically, it's a position vector drawn from the charge generating the field to the location in space. Remember, this electric field exists whether or not there's a charge there. We can calculate the strength of that field, and if we take a charge little q, really let's call this big Q, sorry. If I take a charge little q and put little q at that location, it will feel a force. And we can calculate that force. And if I take a little charge little q and I put it there, that charge will feel a force. An electric force, which I can calculate now that we know by just multiplying Q times the electric field. If it's a negative charge, but equal magnitude, I get the same exact physics, only I get a force that points towards the field, or points in the opposite direction of the field lines, or towards the positive charge. We all good with that? We understand that? Okay. So, as is the case usually in physics, let's take that basic concept and let's make it harder. Yeah. So, we can calculate the field at a point in space based on a point charge using Coulomb's law and using our equation for electric fields. So, what if we have an extended charge distribution? Right? Remember we did that with like rotational inertias, the rotational inertia of an extended mass, right? Extended mass distribution, a disk or something like that. That's where we're getting to now. Okay, so rods of charge, like a rod of charge, or a sheet of charge, or a not a point charge, but a sphere of charge. That's where we're getting to now. And you guys have done Riemann sums at this point, right, in calculus?
Yeah.
And then you learn how to do an integral, and you're like, well, why did I do Riemann sums when I can just do an integral? Right? Have you learned that? You can.
Yeah. I think BC has A, B has A.
Are you doing integrals?
Not yet, no.
Okay. Well, we're about to have some fun. So yeah, are you doing Riemann sums?
No.
Okay. Well, don't tell Mrs. Fudge that I told you that. Because as is the reason I point that out is, as is the case, usually in mathematics especially, you're like, before calculus, you got after calculus. Before calculus, they did stuff that we can use calculus for. And when you did it before calculus, it was really tedious and difficult. After calculus, a lot of things became a lot easier. So, same thing's going to happen here. We're going to learn how to use brute force physics to figure out how to calculate an electric field due to an extended charge distribution. You are required to know how to do that for certain situations, not all situations. And then we'll actually learn Gauss's law, which I kind of introduced last week, to solve these same types of problems a lot more easily. Okay, so that weird integral with the circle on it, right? The circle on it. But again, before we get to that, before we get to our first Maxwell's equations, we got to figure out how to find electric fields due to extended charge distributions. So I'm going to title Tim. So electric fields due to extended charge distributions. And this works regardless of what type of distribution. You could have like a regular object like this faucet up here and put a bunch of charge on it. To mathematically calculate the electric field at a point in space surrounding that would be very difficult. So we limit ourselves to like small sections of rods, area like a sheet, as I said, or symmetrical objects like spheres. And so when we do this, though, as we saw when we were dealing with rotational inertias and centers of mass, and I mentioned this then, it's all about the densities, right? Then it was mass density, now it's going to be charge density. So charge densities are going to be very important when we set up our integrals, just like they were when we set up our integrals for rotational inertias and centers of mass. So we're going to be talking about charge densities, and thankfully, this is a good way of reviewing that stuff because we use the same symbols, right? The symbol lambda is when we have linear charge distributions, so it's charge per unit length. And we have a lowercase sigma, and so this I can say is Q over L. Lowercase sigma, which is charge per unit area, or Q over A, or A is usually length times width, or a circular sheet of charge. And then rho, which is our volumetric mass density, which is what most people think of when they think of density. But whereas it was mass density in mechanics, in E&M it's going to be charge density per unit volume. And remember when we were doing our integrals of for rotational inertia, it was the integrating r squared dm, right? But we had to express the equations, we had to express dm in terms of a quantity that we can actually integrate with respect to, and we're going to have to use the same thing. And so that's why we have these charge densities here, and that's why we have to use them. Okay. So this is linear charge density, areal charge density, volumetric charge density. Okay. And I feel like the easiest way to introduce the process here is with an example. And the example, you might think that we would start with a straight line of charge. Straight line of charge, and say calculate the other. Say I take this guy and I insulate it so it doesn't dissipate its charge into me or into the air. I insulate this guy and put a charge on it, in ways that we talked about by induction or conduction, and say it evenly distributes itself. And it would because this is a metal, right? The charges will evenly distribute themselves. And I want to know the electric field, say, at this point here. Turns out that that's a pretty tough problem, right, in comparison to other examples that I can introduce this with. So instead of doing that, which we will do probably tomorrow, we actually there's an easier example that we can do. Let's say we have a linear charge distribution, but I'm going to curve it into a half circle. I'm going to curve it into a half circle so it looks like this. So here I have a half circle, or a circular arc, with uniform charge with charge big Q uniformly distributed over its length. Distributed over. What's that? Yeah. Neglecting the ends here for a line of charge, it will be pretty much like if you have an infinitesimally thin line of charge and you put charge on it. Actually, it won't, but we assume it was now. It won't. Conductors. It depends on if you're talking to a conductor or an insulator, right? If I take this insulating rod and I charge it with this rabbit fur, but I'm very careful to do the same with the same force over the same section as I'm making the contact and I'm rubbing, then I will get a largely uniform charge distribution.
So if it's like the charge wire in a laser printer, is that like an example of going to be uniformly charged?
Charged what?
The charge wire in a laser printer, has the charge of paper with a smart stick to it. Like there's a wire that's like.
I'm not sure.
Okay.
Maybe. I'd have to look that up. Maybe Johnny knows. And honestly, yeah, I messed up. If it's a conductor with uniform charge, it's not going to be distributed evenly. My brain is, I take 3 days off and I forget all of physics. Because what happens?
It goes to the outside.
It goes to the ends, right?
Oh, yeah.
Oh, the outsides and the ends. Yeah, this is good. Because, yeah, you got all this. Yeah, it's not going to be uniform on this. But if I charge an insular, so this is what I meant to write. Circular arc of insulating material. And we'll talk about when we get to this discussing electric fields within conductors, like on the interiors of conducting objects. We'll talk about this in a lot more detail. But for now, we just want a uniformly distributed charge on this insulating rod that's been bent into a quarter circle or a half circle. And I want to know the strength of the electric field at this point, which I'll call P. Okay? And it's right there in the center. Okay.
Yeah, it's only a row.
What's that?
That's a row.
Okay.
That's a row.
No, it's a P. That's a row. That's a P. Come on, can't you tell the difference? Okay. Now, I don't know if you remember, but when we calculated rotational inertias, or centers of mass, we would take a representative portion of the object, right? This guy overall is charge Q. But I can divide that charge Q into a bunch of infinitesimally small charges, which I will call dq, each one. And how many of those will I have?
An infinite amount.
An infinite number, right? Yeah. So I'm going to, now I can't draw things that are infinitesimally small, so I'm going to draw it macroscopically, but
Why not?
I'm going to take a section of that and call that charge dq. And just like I had up on the board before we started this, I have a positive charge. And if I want to know, if I have a point charge and I want to know the electric field due to that point charge at a certain location, I just draw an electric field vector pointing away from it or towards it if it's a negative charge. So the electric field due to this guy will be this electric field right here. So that's DE, right? Is that? Yeah. So this charge, this infinitesimally small amount of charge dq produces this infinitesimally tiny, teeny tiny electric field dE. Okay. Now, what if I have this charge, the same corresponding dq, but over on this side? And I draw that electric field vector. And the principle of superposition applies. What do you think happens to the x direction electric fields? They go away. Yeah. Right? The component, this guy I can decompose into, and let's use our standard Cartesian coordinate system. This is DE in the y direction. This would be DE in the x direction. And we can say, and very often you have to state this on FRQ, you could say, by symmetry, the electric field, the total electric field in the x direction is simply 0. Right? Because for every charge, for every electric field vector, for every x component electric field vector from charges on this side, they will be exactly offset by charges on the other side. The electric fields generated by charges on the other side. So really all I'm interested in is calculating the electric field in the y direction. Okay. And we pick a circle because a circle, all of the DQs are going to have the same distance to the point in question. So that's a variable that we're not going to have to trifle with. I like that word, trifle. Okay. And now let's write the equation. Let's write the equation for this electric field. Not this one, this one. This one we're not worried about because the x component of that field isn't going to be in our final result. So we want to find an equation for the electric field in the y direction, dEy, due to charge dq. And that's simply 1 over 4 pi epsilon naught, otherwise known as k, let's start with k. let's start with k, but as you'll see in this particular case, we can actually reduce it a little bit if we incorporate 1 over 4 pi epsilon naught. But let's just call it k times charge dq over r squared. But that's not the whole story, right? Because I'm interested in the y component. And so if I do this, right, I get this angle. If I say this angle here, then that will be this angle here, right? Right? And so I want to write dEy in terms of that angle. Well, I can take this vector and put it over here, which tells me that the y component is what? The sine or the cosine component? It's the sine component, right? Right? This angle is congruent to this one here, so that's going to be the sine. Or you can take dEy and move it over to here, in which case it's the opposite component, right? Remember, you can move vectors around when you're dealing with them. So, so that's going to be the sine component. So this will be not k dq over r squared, but k dq over r squared times the sine of the angle theta. Cool beans? Oh, we're running out of time. Okay, we're gonna have to rush this easy part. Now, like we couldn't integrate dm's because dm wasn't the thing that varies, right? When we integrate, we have to integrate over the thing that varies. What's the thing that varies as we add up all the electric fields due to all these charges? Theta changes. Theta varies, right? And so what I got to do is express dq in terms of theta. Well, how can I do that? Well, what I can do is say dq resides on a segment, an infinitesimally thin segment, subtended by an angle d theta, right? Final theta minus initial theta is d theta. It's that infinitesimally small angle there. The arc length is radius times d theta, right? That's geometry. Arc length is radius times angle, right? If we're dealing with radius. And so dq is going to be the charge density times the length on which that charge resides, which I can see here. If I take my lambda, it's charge per unit length. In this case, that length is pi times the radius. Not 2 pi times the radius, that would be the circumference of the whole circle. But the macroscopic, remember we do macroscopic and microscopic. Macroscopic q over pi over r, q over pi times r. The microscopic is just dq over r d theta. R d theta is the length of the segment on which the charge resides. dq is the amount of charge there. And so I can use that expression to express dq, charge dq, in terms of charge density lambda times the radius times d theta. And so I can make that substitution in for dq. And so the differential electric field, the y component, which is the component that we're interested in, is k times lambda radius d theta over r squared times the sine of the angle theta. And then to calculate the total, we're going to do like 3 or 4 of these examples over the next couple days. So this is a lot to take in, I know. And then I just integrate both sides. When I add up all of the electric fields at y, at that location, I just get the total electric field in the y direction, which will be the total electric field because all the x components cancel out. And then what are my limits here? What am I integrating? Where am I going? Where do I end? 0 to pi. So I'm just going to integrate this from 0 to pi. But I can pull all the constants out. First of all, that r cancels with one of those r's. K is a constant. Lambda is a constant. R is a constant. I can pull all that out. And then I'm just integrating from 0 to pi of sine theta d theta. Who said that? If you haven't done integrals because you're an AB already, that's okay. But what's the integral of sine theta? D theta. Negative cosine theta. Yep. So this result will be K lambda over R times negative cosine theta. I guess I haven't evaluated my limits yet. Negative cosine theta, evaluated from theta equals 0 to theta equals pi. So that electric field is going to be K lambda over R times negative cosine of pi minus negative cosine of 0. So the electric field then is K lambda over R. What's the cosine of pi? Negative 1. And the negative of negative 1 is positive 1. What's the cosine of 0? So minus a negative 1 plus 1. So I get that the electric field in the y direction is going to be, doing this right, aren't
I hope so.
2K lambda over R. Okay? And then if we substitute, we have an equation for lambda in terms of the overall charge, and that's usually the substitution we make. We can plug in Q over pi times R in for lambda. So that's going to be 2K times Q over pi. That'll end up being pi R squared, right? Yeah. So that is one way of expressing that. Since we're about out of time, I'll start the other way. But we can substitute 1 over 4 pi epsilon naught in for k, in which case I would have 2q over pi r squared times 1 over 4 pi epsilon naught. So that 2 cancels with that. And I got a pi squared. Okay. Yeah, we'll start there. As a brief introduction, we will do this quite a bit for the next couple of days. Have a good day.